Ok, we start. Buonasera e un cordiale benvenuto all'ottava edizione di Digital Humanities, Theoria e Methodologia. Guten Abend und seien Sie herzlich zur 8. Auflage der Vortragsreihe Digital Humanities, Theorie und Methodik willkommen. Good evening. I welcome you all very cordially to this 8th edition of the lecture series Digital Humanities, Theory and Methodology. As our guest is not fluent in German, English will have to be our language of communication tonight. You can, however, also ask questions in Italian and German later, and together we will try to do our best to make everybody understand and to follow. I'm really happy to say that this edition of the lecture series is for the first time a real joint venture of the Saxon Academy of Sciences and Humanities in Leipzig, the Forum Digital Humanities Leipzig, and myself, Emeritus Professor of Romance Linguistics and still member of the Institute of Romance Studies at the University of Leipzig. In former years, the lecture series was already hosted quite a few times by the Academy, but the Forum of Digital Humanities Leipzig was not part of the arrangement of the event. Before I say a few words about the lecture series itself and introduce our speaker to you, I would like to thank first of all the Saxon Academy for Sciences and its General Secretary, Dr. Christian Winter, for their generous hospitality and proactive collaboration, and especially Uwe Kretschmer, without whom the collaboration with the Academy would not have come about in the first place. I would also like to thank Dr. Kerstin Hohner and Veit Waldeck for the logistical and technical management of the event, and Agnes Silberhorn for the beautifully designed announcement of tonight's lecture on the website of the Academy, and the care with which she handled the abstract and its contents. And last but not least, I would like to thank Veit Waldeck again, who is responsible for the recording of our event. The recording will be made available to the public in the YouTube channel of the Saxon Academy, as well as in zeno.org, where I have created a so-called community, Digital Humanities Theory and Methodology, for the lecture series. And I think nobody has to feel apprehensive about the recording, because only the speakers in front will appear in the recording, as far as I know. The lecture series, Digital Humanities, Theorie und Methodik, or Theory and Methodology, was founded in the winter semester 2014-15 with the aim in mind to fill the term Digital Humanities with contents and to present theoretical and methodological questions of this new epistemology to a broader public. This endeavor felt really necessary then, because most colleagues and students did either not know what Digital Humanities was about, or tended to use the term when they referred to all sorts of media-related fields. That this has changed in the meantime does not mean, however, that this lecture series has become obsolete. Quite on the contrary, now that not least because of the success of ChatGPT, artificial intelligence has become a real hype, and the rapid developments in the domain of generative AI, and especially large language models, pose many questions with respect to education and formation, as well as for research. And now that this is the case, the epistemological foundations of digital humanities come to the focus again. And I'm really happy and satisfied that we can dedicate tonight's event to the relationship between digital humanities and generative AI, and discuss critically the possibilities and challenges their integration presents us with. We are really lucky that we can do this together with an important representative of the Italian Informatica Umanistica and a sharp thinker like Fabio Ciotti. Should you wonder why I use Informatica Umanistica when I refer to the Italian branch of digital humanities, then please go to the recording of the lecture Fabio gave in 2018 about the historical development of digital humanities in Italy and its paramount contribution to digital humanities generally. You can find the recording in the Zenodo community, Digital Humanities Theory and Methodology. Only when I prepared this short introduction, it dawned on me that 2018 means 6 years ago, and that November 2018 was also the last time the lecture series took place in this lecture hall. The COVID-19 pandemic was disruptive also with respect to the lecture series. And I'm so glad that Fabio accepted the invitation and is actually back here and with us tonight. Let's welcome him very cordially. I met Fabio for the first time in 1998 at the first International Computers, Literature and Philology seminar in Edinburgh, where he gave a talk on text encoding as a theoretical language for text analysis. Fabio was then working with Giuseppe Ciotti, who in 1993 had founded the Centro Ricerche Informatica e Letteratura CRILET, perhaps translatable into English as Research Center for Informatics and Literature, at the Department of Studi Filologici, Linguistici e Letterari of the University of Rome, La Sapienza. Giuseppe Ciotti was also the supervisor of Fabio's thesis on Trattamento informatico del testo narrativo, memorizzazione, codifica e analisi dei tempi verbali, né il turno di Luigi Pirandello, with which he graduated. I'm sorry, but I need to name this thesis, not least because every time I come across its title, I remember with melancholy my own fascination with the usage of verbal tenses in Romance languages during my studies and right up to my PhD project, in the framework of which I was forced to create an electronic corpus of Italian newspapers if I actually wanted to do the research. Now, let's leave the past behind and come to the present again and to Fabio. Fabio Ciotti is Associate Professor of Theory of Literature at the University of Roma Tor Vergata, where he teaches cultural analytics and computational literary studies. He has been working for many years on the methodological and theoretical aspects of digital humanities and computational literary studies. He has recently worked also on the impact of generative AI in humanities studies. He's the author of numerous publications, including the recent volume Digital Humanities, Metodi, Strumenti e Saperi, published by Carocci in 2023. I can hand it over to you and you can have a look at it afterwards. Fabio has participated in various research projects at the national and international levels and has been organizer or member of the scientific program committee of various national and international conferences. He was also the chair of the program committee of the Global Digital Humanities Conference, which in July 2019 brought together in Utrecht 1,066 digital humanists from around the world, and was, as it later turned out, to be the last on-site digital humanities conference before the breakout of the pandemic hit also our conferences. Fabio Ciotti is editor-in-chief of the journal Humanistica Digitale and has been the chair of the EIDH, European Association of Digital Humanities, executive board and president of the Italian Digital Humanities Association, AUGD, which stands for Associazione per l'Informatica Umanistica e la Cultura Digitale. Fabio Ciotti will now give his lecture on digital humanities and generative AI, yet another methodological turn. Fabio, the floor is yours.
First of all, I want to thank the Academy and the Forum for the invitation, but especially Elizabeth, with which I shared the last 20 years in the governing body of the global digital humanities. And we also spent not only a lot of time discussing about political and theoretical issues, but also enjoying ourselves and sharing a friendship that has been lasting more than 30 years now. So it's for me a great occasion to see her again, because now she's retired and she doesn't, we don't have many occasions to see like before. Yes, this presentation is the results of the work I've been doing the last couple of years, 3 years, after the introduction of ChatGPT that has changed the world as we know it, at least for many respects, and especially for the impact that it can have, in my opinion, to our way of understanding cultural objects and processes via computational methods. And that's why using anyway an interrogative stance, think that we may be in front of another methodological turn. I've been in the business of DH, or Informatica Umanistica, as we call it in Italy, since 35, or not 40 years now, sadly. I better not to think about it. But anyway, since my master thesis and in the 90s. So I've seen many methodological turns. I've seen many change or turn into the way we think our relation as humanists with technologies and especially with computational methods should go. And I also worked in various projects, so I also try to see how this theoretical stance can also drive the way we make actual projects and so on and so forth. So this has been my main interest. And that's why I think that we are in phase of something that is important. My talk will be about AI, and I will also say something in general about AI. Probably most of you know better than me some of the issues that I will present, but it's better to give a complete frame to understand my kind of discourse. So, first of all, a very fast picture of what has happened in the last 30 years in DH. First of all, DH, because DH is a term that has been introduced, as you may know, only at the outcome of this century or millennium. Before we use different terms, humanities computing in the global or English Anglo-Saxon community. In Italy we used Informatica, we still use Informatica Umanistica. Computer philology was the term more common in Germany, and the fact that in 2003 was adopted this term was a turning point in many respects, because using the term, for instance, Italian term, Informatica Umanistica, we were more looking at the aspect of how to process humanities data with computational methods. The problem how to represent those data was important, and modeling was one of the central core of our discourse, but was not the final destination of our efforts. Then, using digital, changed this aspect. At a certain point, we have seen that most of the projects around the world in DH were more about representing stuff than trying to understand them using pure computational methods. And this was good, because it was also a way to enlarge the community up to the point that it has become one of the big discourse in the research in the humanities of the last 20 years. And also the community has grown a lot. I mean, when we met in the early 2000s or late 90s, conferences had something like 20, 40 people at max. My conference, the conference that I was chair of, had, as Elizabeth said, more than 1,000 people and something like 600 presentations. It's still the bigger, because the conference after the 2019 edition were a little bit smaller. Well, apart the fact that in the 3 years of the pandemic, there were was no face-to-face conference, but we are still the biggest, and that's what sort of, for me, it's an important thing in a sense. So, the second thing that has happened in the last 30 years is big data. That is, we have now, and we have been starting having since the at least the start of the century, a lot of data to work on. Historical data, because of the huge digitalization projects, partly done by academic institutions, partly or even the most part done by private or institutions like libraries. Google Books is one of the most common examples, but we had a lot of resources to work on. And of course, there are also not historical data, so all the amount of data, the cultural data that we produce in everyday life. So Twitter and social media and whatever, and blogs and all the forums that have risen in the net provide a lot of data that we can study to understand what is happening at the cultural level in our era, with all the problems connected to it. And of course, we had to find methods to analyze this kind of data, and that's where computer science people gave us a lot of tools, especially in the last 20 years. Not all of them were developed in the last 20 years. There are some methods that are commonly used, like stellometric analysis, that adopt methods that were projected and developed even in the 60s. But anyway, it's only in the last 20 years that we saw tools or methods like topic modeling, in general text analytics for big data that we couldn't use or afford to use before. And from that, this new discipline, a sort of discipline, data science has emerged. And there is the humanities version of data science, that is cultural analytics, that is something proposed by Lev Manovich as a term, but that has been also adopted. There is also a journal that is called Cultural Analytics to indicate this kind of endeavor, that is trying to understand humanities data, a lot of humanities data, using very hard computational methods. And this is what happened in the last 20 years, more or less. I should add the notion of distant reading by Moretti, that is another term that has been used a lot in my community. I am, of course, my background is literary studies and literary theory, so distant reading was an idea that has circulated a lot in my community, my stricter community. That is trying to understand how text, and literary text especially, works without reading them, but trying to apply to a huge amount of text this kind of methods to get something from them. And finally, in a couple of 3 years ago, AI came back again. And I started from AI. With Giuseppe Giuliozzi at the time, we were working on a LISP program that tried to understand how short narratives, of course, because we had to prepare a lot of data, and you had to do it manually, and you had to program all the stuff that you were using. So we were just playing with toy experiments, but we started with using tools that were coming from classical AI. So after many, many years, I came back to AI with this new kind of AI that we have now available, and started to think about what is happening. First of all, what is AI? And it's a discipline, better an interdisciplinary field of study that tries to analyze artificial systems that are of computational nature, although, we have to agree what computation means, but anyway, I think that what is important here is not the technicalities of programming in Python or whatever something, but are the mathematical methods that are behind, or the computational/mathematical methods that are behind. The perform task and activity that requires the use of what we call intuitively intelligence. At whatever level we may imagine this kind of intelligence is applied. And this is a citation from one of the big men of old GoFi and artificial intelligence, Feigenbaum, that restate what I just said. Classic AI was born in early 50s. Actually, probably the first, the starting point was the famous article by Turing, Computing Machinery and Intelligence. But the formal foundation of this discipline was the famous seminar of the 56 organized by McCarthy, and where some of the big men of the AI, of the first at least if the part of the history of the AI, were invited, like there was Shannon, there was McCarthy himself, there was Marvin Minsky, some people that has done a lot of work then in the succeeding years. And the basic assumption of this first round of AI was that intelligence is a set of high-level skills that are fundamentally linguistic and logical. That is, they are based on the manipulation of symbols. The idea that reasoning, this is an old idea that we can trace back to Hobbes at least, is something that in general can be similar to a computation in the mathematical sense. That is the application of rules to a set of symbols to obtain certain results using an algorithmic approach. And then there were some more philosophical issues that contributed to the development of the first round of AI, the the good old-fashioned AI. The idea that the mind works operating on some kind of representations that we may call symbol, that has a causal role in our cognitive behavior. The immediate counterpart for this idea was the Turing machine, that is, something that actually has a material constitution, has no metaphysical intricacies or mysteries behind. It's a tool that works, and that can do complex stuff like doing calculation or computing numbers, but also, and Turing said immediately this, doing some more complex stuff like working with language or translating. These were the ideas that were already circulating at the time. And there is this other philosophical contribution that came mostly from the philosopher Hilary Putnam, the idea that intelligence is independent from the substratum of the object that is presenting this property of being intelligent, that is called functionalism. So it's not important that to be intelligent you have a brain made of cells and biological stuff, or a mechanical object like in the the difference engine by Babbage, or something that is built by electronic stuff or whatever kind you may imagine. That really doesn't make any difference. What is important, trying to understand the function of these devices, how they interrelate, and how they implement this idea of applying rules to symbols. Okay? This was the idea that was at the base of classic AI. And they started to work immediately on some kind of complex tasks, like translation, because they had money for that, mostly. Problem solving, seen as, well, we have a set of possible outcomes of our action, and we must individuate which is the best way of solving a problem in this set of different outcomes. And of course, language understanding. They tried hard, but never succeed in doing anything that was really general as much as we see now. The most one of the most known programs that was there was Chardelieu. Chardelieu was working with language in a sort of toy world, virtual toy world, in which it could, made of pyramids and parallelepipeds and simple stuff, anyway, that it could see, virtually of course, it was described in mathematical form, it could move, it could answer to questions about that world. Very simple, they called it micro words. And they managed to make this program work and answer to questions, but when they tried to scale the approach, that is defining the set of rules that govern our use of language, they didn't succeed at all. They realized that this way of trying to simulate, emulate, rebuild intelligence couldn't work. And that's why they realized, someone realized that this endeavor totally couldn't work, couldn't bring anything substantial, especially for the business, and they cut the funds. And so we have the first big winter of AI. In the same years, there was a proposal of a different paradigm, not totally different, because we must not overemphasize this here, but anyway, a different paradigm. That is the idea that if you want to have an intelligent machine, you must try to model and simulate the biological system that presents this property as much as you can. And since we know that the only object in nature that has the property of being intelligent is the brain, and the human brain in particular, not only the human brain, because there are some kinds of intelligence that are also in some animals, we must simulate how the brain works. And at the time, they already knew that the brain was made of cells that were interconnected. I'm reading the autobiography of Daniel Dennett, my philosopher of choice, and that is telling this story from his point of view. He was a philosopher, of course, and it's really interesting how these ideas were trying to emerge in those periods, in the 50s and 60s. The first idea of having a computational machine based on the notion of a net of very simple computational units was in this paper that predates the creation of the first working computers. So this is the famous article by McCulloch and Pitts, A Logical Calculus of Ideas Immanent in Nervous Activity. But here we still have a very strongly logical way of seeing. The network imagined by McCulloch and Pitts were formally logical calculus. Only some years after, Frank Rosenblatt, who was a psychologist, imagined this different kind of network that he called perceptron, that he implemented in a physical machine. So in another set of slides, I had a picture of this computer that was governing his perceptron. And for the first time here, we find some of the most important ideas that are behind the current neural network that we see that are behind these models. And the basic theoretical assumption was that intelligent behavior is emerging from the complex functioning or behavior of a network of very, very simple computing units, just like neurons. In neurons, we don't have any intelligence. Billions of neurons together produce what we are. So we have to, reverse the process. Instead of looking from the top and going to the, trying to go down until we find where intelligence resides, we must reverse the process, so to have a bottom-up approach. And there is a sort of functionalism also in neural network research because, of course, artificial neurons are not neurons. Their work is much simpler there, at least for what we know, the way in which biological neurons works, so it's an abstraction anyway, but it's a very lower level abstraction than in the classic GoFi. And then another important idea that you cannot program intelligence, you cannot find algorithm of intelligence. You can maybe try to model some very subset of intelligent behavior, playing chess, or trying to understand language in a very restricted environment. But that doesn't scale. This kind of approach, the purely algorithmic logical approach doesn't scale. So you have to find another way that is similar to the way we learn to do intelligent things. Apart from the fact that we probably have in our brain a lot of stuff are coded somehow. We don't know very well how. So you have to train these computational artifacts to do stuff. At the time, it was not clear how to do that. There was no a strong mathematical theory of how to train a network. This came only later. But anyway, this idea was very interesting because you had no strong assumption on what intelligence is. You try to build something that learning, doing stuff, acquire emergent properties. And of course, then there was the concrete development of this kind of computational artifacts that are called artificial neural networks. And most of these early neural networks were mostly or almost exclusively prediction or classification machines. And this has been true until the last 10 years. And this is a representation of what a neural network is. We have the idea of having this sort of nodes that are actually very simple computational machines that do additions or calculate simple functions. These nodes are connected with other nodes, and these nodes can exchange between each other signals, very simple signals, simple numbers. And what makes this very simple tool or system interesting is the fact that using this notion of a parameter or a pound, you can adjust the way that each neuron reacts to the input signals, and then, of course, output give birth to an output signal. Sorry. So when you hear about parameters, say we hear about billions or hundreds of billions or thousands of billions or trillions of parameters, we actually refer to this small number, that W that you see there, that is simple, a number by which you multiply the input signal that is also a number. Then you may add a quantity that is called bias, but this is a technical stuff. And then you compute a function that says, well, given these inputs, this is the output. And you can have a very simple output, simply the result of the addition in the first elementary neural network. Now, instead, there are more complex functions that translate these input signals into something that resembles a probability measures. So we have functions that translate the addition of these signals plus the bias to a continuous function that has a domain between 0 and 1. But this is technical. Anyway, this is the idea. It's not very complex. As you see, it's very simple. Actually, the math behind this is also very simple. But when you put together thousands, billions, hundreds of billions of this stuff, you get interesting results. And you get interesting results because you can imagine different complex structure of these networks. The original perceptron was only a two-layer. There was a set of input nodes, and then there was a set of output nodes. Then they added more layers between the input and the output, so we have the multi-layer perceptron. Then, of course, the research went on, especially because there was a more formal definition of how to train these networks using the famous back propagation algorithm. That is an old idea that was circulating in the statistics since the mid of 19th century, that was reframed for computational needs. And this idea was very interesting because it was a general method for educating a net. A net that can be complex as you wish. And of course, these different topologies of networks can have much more complex capabilities than the original perceptron network. And there are a lot of type, that is convolutional networks, that were very important because they were the first that were able to recognize images. Then recurrent or long-term, short-term memory that were very important because the word that were able to elaborate language that has the problem of being a sequence of signals. And in neural networks, usually you give the input and you have an output that is a yes, no, yes, probably, no, probably, okay? But the input is all given one at a time. And all the set of the inputs are processed all at once, at each step of the processing. Language has the problem that it starts here and ends here, and you should read it sequentially. And this was not very easy to process. That's where recurrent network came. But the problem with recurrent network was that they are really demanding in terms of computational power. and they couldn't scale, treating big chunk of text. And okay, the idea of learning is also very interesting because, as I said, neural network cannot be programmed. Actually, you could take a very small, simple artificial neural network and adjust the parameters by hand. This can be done. If you have 10 nodes, 15 parameters, it can be done. You cannot do that, of course, if you have a very big network. This is how, for instance, the first perceptron was actually educated in recognizing the environment in which the robot was. It was connected to a robot in which the robot was moving the edges of the square where the robot lived. So you cannot program them. Of course, there is an algorithm for, or there are some models that we can use, or we have seen, to set up the starting point of the net. But then what you have to do is showing thousands or tens of thousands or millions or billions of cases that must be labeled and must be labeled by a human, saying these are positive cases or these are negative cases of what you want the network to recognize. And then you show them, the networks will start saying strange things, and then you can measure the distance between what you expect and what the network is saying. These are all numbers. Of course, we interpret them as you recognize the face of a cat or of a dog. Actually, what happens is this is a probability gradient of what I derived, the net derives from the input. And we can say, well, he says that probably this is a cat by 99%, okay? But at the start of the learning process, the probability of that the net will output are very low, very far from what we expected. Since it has a number, we can measure a distance, and we can use this distance as an input to the backpropagation function that, via a very complex calculation of the derivatives, can adjust the parameters. And this process, this is a process that must be redone various times until the net stabilizes with a good performance. Never a performance that is perfectly, exactly fit to the task. So you will never have a network that is always functioning with all the possible input cases, and this is totally different from what an algorithm is. That is exactly a process in which, given some input, you already know from what kind of output can be generated, although you may not calculate it by hand, but you are in a perfectly deterministic process. Here, you are not in a perfectly deterministic process. Okay. What is the difference with generative between the post-classical neural networks AI and the generative AI? First of all, it is the same technology. Mostly is based on the same ideas. It is these neurons that calculate functions and addition, multiplications, and some sort of function for the output. But the difference is that here the system can generate new data. You are not only judging something, or the net is not only judging something, saying this is a cat, this is a dog, it's generating new data. Actually, we can also understand this kind of generation as a way of judging something, because at the end of the game, what is happening in an LLM is, well, given this input, I predict with a certain amount of probabilities that the next token, the next word, that's simplified, they are not really words, but the next word may be this. So in a sense, it's also a classifier. It classifies the probabilities for all the words that the system knows that they follow a certain sequence in input. Okay? But anyway, the end of the process is that it produces new data. And this kind of systems are based on very large neural network architectures. They must be very big because to be trained in doing that, they must read a lot of input data. And so the number of parameters necessary to model this complex set of input data must be very big. And we know now the result of this idea, that is Claude, Gemini, Llama, and of course GPT. Among the generative AI systems, the most interesting, especially for us, are these language, big or huge language models. And as I said, these are systems that produces text in response to text. Abstract, at an abstract level, we can say that is a system that is capable of predicting the most appropriate sequence of linguistic or other kind of tokens on a probabilistic basis, starting from a given sequence. So, to be more precise, given that you give in input a sequence, T1, Tk, the system, the net, estimates the probability distribution of all the terms that he knows, all the tokens that he knows. So he has a vocabulary that is fixed. He learns during the learning phase, and then that is fixed. And then for each time we give a text to the system, to the net, it estimates the probability that out of 50,000, 100,000 possible continuation, the first one in this vocabulary has the probability X to be the successor of the input stream, and so. And then make a guess of what is the best output that I should give back to you. Actually, not to you, because the system is autoregressive. That means that the output of the first process is given back to the net so that it can go on generating. Otherwise, it would stop at the first generation. So that's why they call it autoregressive, because simply it's a process that is sort of recursion, not technically or logically recursion, but anyway, a sort of recursion. So the output of the first generation is given back as a whole to the system, and it goes on until it finds condition for stopping. The base of this kind of language networks is the idea of word embedding. This is something that has been also circulating in the debate of neural networks since the early 10s. That is the idea of representing semantics of language using a very big vector, that is a sequence of numbers. How can you put these numbers inside this vector? This is the vector, a part of the vector for one of these early systems, that is Glove, for the word king. How can you derive these numbers? You see are real numbers, at least the kind of real numbers that can be actually represented in a computational tool that has finite nature, of course. This is an operationalization of an old idea. That if you want to understand how language works, actually how language works at the semantic level, you must look at how language is used. So if you look at tens, thousands of contexts or use of a word, you can derive an idea of what is its meaning. There is no mysterious property, no kind of metaphysics semantic level behind. There is no behind, actually. It's all in the language itself. And this idea has been developed in the 50s by Firth, especially, but many others were working on that. Somehow there was a sort of this idea also in the second Wittgensteinian philosophy, the notion of meaning as use, although Wittgenstein was much more complex than simply saying that you must look at the linguistic context. But anyway, given this idea, if you find a way to present to a computational object, very simple, many contexts in which you can find a word, masking that word, and saying, well, you must imagine what kind of word is there. I masked the word that you want to model. Using a simple neural network, you can derive this kind of structures. Okay? This is the basic idea of the current language models. Translating the meaning of a word into a set of numbers, a vector of numbers. And since this is a vector of numbers, then you can do very complex stuff with these vectors. And this is what happens with LLMs. LLMs are built on this idea, adding a complexity. When we speak or understand language. We do not understand the semantics of any single word or token in isolation. We understand them in the context of that specific expression. Okay, what Saussure called la parole. Okay, so if you want to understand how it is used a word in a specific context, you must also keep trace of what has been said before. Otherwise, you cannot solve very important aspects of language like co-reference, or why you are using a word in a specific place instead of another. That is how you make a choice, again, comes back Saussure, in the paradigmatic axis of language. You can have many possible choices when you say something, and you select one. So, but if you do that, it's because you look at, or you think of what you have said before, or you read what has been said before, and try to imagine what you can say. And this is actually what LLMs do. And this problem was solved using this idea of attention, that is the most important aspect of the neural networks that are behind LLMs. And saying it simply, it's a way to say, okay, if I must continue it's impossible to read it here. So the sentence, the first token is starting. Yeah, here we start, okay? It's a formal token to say, well, you are starting here a sentence. Then a robot must obey the orders given, okay? How can you imagine what can follow? Well, you have to, for instance, individuate which word can have a role in determining which token or word adding here. And this is what attention does. That is, attention tries to give a weight again to every word of the sequence before the word that you're actually looking at or do you want to produce, trying to understand which of the preceding tokens or words have a role in determining this production or the meaning of this word. In this case, we have a robot have the highest probabilities because it is a pronoun, and so it needs to be a co-reference of something that has come before. And there may be many words that have a role in this, but probably the first words are a noun and an article that have a role in determining it here in this sequence. So this is a sort of calculation of, given a string or a set of words, what are the probabilities that any single word in the string contribute to the meaning of the last word that must be produced. I'm really making it very simple, but the mathematics is not very hard to understand. If you are not good at math, you have to study a lot, but anyway, it's not very hard. So a transformer is something like this, and it's a building block of LLMs, something that takes in input strings, translate them into tokens, translate each token into a numerical representation, a word embedding fixed like the one we have seen before, then starts looking at these embeddings and tries to calculate how each embedding can contribute to the meaning of the last word it has to generate. Then he, at the end, gives a distribution of probabilities for all the words or tokens that he knows, and then make a guess. Actually, to make these systems more creative, the final output is not governed only by the selection of the most probable words, because the result would be that at any iteration of the system, at any prompt you give to the model, it would answer exactly the same thing. And that would be weird. So that to avoid that they repeat themselves endlessly, they introduce some level of stochastic decision at the end of the process. There can be very techniques for doing that. Actually, the idea is, well, you select the first n most probable words that can be the proper continuation of the input string and take one by chance. Or you can adjust various parameters, that is, for instance, temperature, for how to distribute these probabilities among the various words, so to avoid very big difference between the distribution of probabilities. Anyway, there are various techniques for doing that. And this is a parameter that can also be controlled somehow in language models. And in this way, it outputs a word, and then it starts again. It gives all the resulting string, that is the initial string, the prompt, plus the first word. It goes back in the input and goes on until it finds that is satisfied. And it means that it finds some tokens that tells him, you can stop. You have answered in a correct way. This is the basic level of working of these kind of systems. But then, how is it possible that they can understand what we tell them as instructions? They can do very complex stuff like, I don't know, having conversation about any kind of issues that you can imagine, and so on and so forth. I mean, this very basic way of functioning doesn't solve, doesn't explain all the capabilities that they have. And in fact, the very important contribution of the people from OpenAI, that were the first that managed to do that seriously, is not the idea of transformers or autoregression in token production or generation. There was an idea that has been published in an article of 2017 by a group of researchers from Google, and that was at the base of the development of the first language model that was BERT. But BERT didn't have none of the capacities that we see in GPT or other kind of models. The idea, the contribution of the OpenAI team was the idea that the training of these systems must be much more complex if you want to attain the capability of following rules, of answering, and so on and so forth. That is, the first phase is the pre-training, okay? And that is the phase that I have roughly described. That is, you give to the system a string. The string is composed of a set of tokens. You wipe out the last tokens, and that's the target of the generation. And you ask the net to generate a possible token that continues the input, the original input, minus the last word. And then you measure how far the word that actually it generates from the word that was in the string. In this way, you don't have the need to label manually the input for training these networks. Because before this idea, you had to hire people, paying them, subpaying them, to see thousands of images of cats and dogs or semaphores. We do it usually when we have to say, we are human, believe me. And, yes, sorry, sorry. I will stop. No, don't worry. I will stop moving. And have a very big set of label data, okay? But that would be impossible for this kind of work, because the number of tokens that you have to present to a network or to a network behind a language model is in the order of tens of billions of words. And imagine how long it would have taken to say, well, this is the correct continuation of a string. But that's not really necessary, because the output, the desired output of a text is inside the text itself. It's the last word. So this phase is the pre-training, and it takes a lot of time, a lot of energy, a lot of money. And it's done once for all, okay? They take billions of words, usually from the net, from the web. They do some kind of pre-processing to polish we don't know what, because they don't publish anymore anything, at least the big models. There are a lot of small models that are perfectly documented. And there are also some data sets that can be used to train models. So if you want to play, if you have enough energy, computing power, you can do that. And they train the model, okay? And for models of the dimension of GPT-4 or Cloud or Gemini, it can take many months. And when it ends, you have a base model. But this base model cannot make a conversation, cannot answer to questions, cannot solve mathematical problems, nothing of that. Usually, when you use that kind of model, you get out a lot of gibberish, of strange. To teach, how many commas you may put, it's up to you to decide. To teach the model to behave correctly in a conversation, you have to show him what is a conversation, how to answer to a question, how to follow an instruction. And this is what is done in this phase, that is the supervised fine-tuning. Here comes back again the necessity of having labeled data. Correct answer to questions. Who was the inventor of general relativity theory? Albert Einstein. Okay? These data have to be produced by hand, by human. Of course, once you have them, you can reuse them many times, and this is what is happening now. And in this phase, the models learns how to follow instruction. Don't ask why this succeeds. Even they don't understand well why this succeeds, but this is actually what is happening. The model learns to answer. You show many examples of question and answer, and knows, well, that's a way to answer. But the interesting aspect is that it doesn't only learn to answer to those questions, it learns to answer in general. And this is what they call an emergent properties. And then they added a third level, and this is what is really interesting, because here is where the research now is pointing. For instance, the last generation models that have the reasoning capabilities are all based on an extension of this idea, the reinforcement learning. That is an old idea. Again, it comes from behaviorism. If you want to teach a dog to do something, you just give a treat if he does the right thing, or you shout, at least I hope, only shout at him if he doesn't. And you do it many times. So you learn to individuate which is the good behavior and the bad behavior. They do a sort of similar thing for models. That they usually, the thing is like this. You ask the model after the supervised fine-tuning something, and you ask to give a number of responses, let's say 4. Then there is a human that labels these answers, giving them a mark. Oh, this is a good answer, this is a so-and-so mark answer, this is a very bad answer. Okay? And then you use this data to train another small model that then you can use to give a final learning phase to the model that you have been training, okay? And in this phase, you can teach many interesting stuff. For instance, not to say bad things about women or black people. Because if you ask the model after the supervised fine-tuning, that is after he has read a lot of stuff from the net, where you can find anything, you know. Then they have shown him some thousands or hundreds of thousands of answers to questions, mostly technical issues. And then you ask something that, what is the right place for a woman in modern society? You will probably have the answer. Well, the proper place to be is in the kitchen, preparing food for his man. Because it is most probable, or one of the most probable things that he has learned in the first phase. So you have to say, no, this is not correct. You cannot say that. And this is the way they do it. That is, they ask him, what is the role? And he says, probably, one of the answers will say that horrible thing that I just said. One of the answers will be now they can do whatever they wish, and they are able. And you say, well, this is the correct answer, so you give a higher mark to that answer, and then use this data to adjust the parameters, and at the end we have GPT. That is very, at least until now, has been very politically correct. Now we don't know what is going to happen in the future. But if you ask this to a Chinese model, of course, we will give different answers, probably. Because here we simply transfer our ethical attitudes to the models. But of course, you can also teach him how to demonstrate a theorem.
which is the best next move in a demonstration. You can teach him many, many different stuff. And this is the way GPT has learned to be not only a good answerer, but a good companion for conversation, normally able to be very, to accomplish your desire, even too much. Sometimes I really would like to say, you are wrong, this is a bad way of solving this problem, because this is the really interesting thing. And so on and so forth, okay? This is what LLMs are. So we have this idea of being adaptable and sensible to the context, that is able to answer to what you ask them, also able to learn from what you ask them. That is, when you present in a prompt some information, it can use that information, adding that new knowledge to the knowledge that he has already fixed in his parameters, that cannot be changed, unless you start from scratch, spending billions of dollars and consuming thousands of kilowatts for training it. The problem is that these things that he learns cannot be memorized. It's just like the protagonist of the film, the movie Memento. He simply forgets whatever you tell them during an interaction. But in the context of your interaction, that information can be used by the model. It can learn from that. It can add knowledge. Okay? So we have contextual learning and prompt sensitivity. This is also an interesting and unforeseen capacity. If you ask him to behave like something, he behaves differently. It, he, okay, she, I don't know, the kind of pronouns using its kind of complex issues. The system behaves differently. And this is quite interesting because nobody has used any specific learning data to tell the model. They ask you to behave like a professor giving a lecture, answer with this level of complexity. If you are someone that is speaking to a child, use this level of complexity. But this is what actually happened. That is, they have kind of personas. And there is a lot of research for trying to understand why this happened. And one idea is that, well, at the end of the learning process, all the three phases, especially the first, but this complex set of billions and millions of parameters implement the knowledge that they have learned. And there is everything there. But during the generation, there are some kind of paths that can be activated that can change the way that the model, in the way in which the model reacts. How it really happens is hard to understand because it's almost impossible to see what is happening during the inference time in these models. There are billions of parameters that are calculating functions. So the complexity of computation needed to understand what is happening is so huge that it's bigger than the model itself. And to work, these models are using a power of computation that you cannot even imagine. So it's impossible. They are doing experiments with small models, and they sort of understand how things may go, but for the moment, nobody can look inside GPT and say, oh, well, that's the neuron that justify this output. Or the set of neurons justify this output. This is impossible at the moment, and probably will be impossible forever. Just like we don't know which neurons are actually the cause of our behavior, or our linguistic, emotional, or whatever behavior. So, what are these tools? What are we in front of? They are complex systems, so we can study them under different perspectives. Of course, you can, adopting different theoretical, also theological, why not? This is interesting. I've been discussing with one of the superstar of Italian AI blah blah. I call it like that because it's not real discourse, but it's mostly a blah blah. But anyway, that is actually I didn't take the time. No, I'm already there. I'm sorry. I have to run. But you can study from different perspectives, okay? So, of course, from the technological point of view, engineers build this kind of stuff and need a lot of competence for doing that, for making them work, for making them more efficient, and so on. From the cognitive point of view. Are they somehow similar to us, or under some respect similar to us? What are their cognitive properties really? Do they really understand something or not? Do they really have beliefs or not? Are they intelligent in general or not? And this is something that is really complicated. And then, of course, as techno-social technologies, that they have impact on our everyday life, and then we know very well that they will change the way we work, and they will also devour a lot of workplaces. Now, what kind of cognitive agents are LLMs? This has been one of the crux in the theoretical philosophical debate in the last 5 or 10 years. And there are many questions that we can ask, as I said. Do they have real semantic competence? Do they really understand language? Do they have beliefs? Beliefs about the truth or falsity of proposition, for instance. Desires, motivations, intentions, they are committed to pursue a certain objective. Do they have intentionality in the philosophical sense? That they have a semantic stance against reality or language or not? Do they have agency? No? Well, this debate has been very heated, as I said, and you can find positions that are, no, these are stupid, even not stupid, because saying that something or someone is stupid presupposes that there is an intelligence that is somehow degraded, okay? Now, they are not intelligent. They have no any kind of human capacities or human-like capacity. And then there are optimistic stances. The most famous negative position is that one that you have probably already seen, the famous Parrot paper by Bender and company. Actually, the real paper that was interesting about this was written by Bender and a colleague that was called Kohler 1 year before, and in which, but the paper about parrots became famous because of the parrot idea. They are stochastic parrots. They are just like parrots that are doing, saying things without understanding any word. Stochastic because they are based on probabilities, although there is a misunderstanding in my opinion. But anyway, this is the citation of the paper that says that they are not grounded in community, so they are not real. No? This is the subtext, communicative intent, any model of the world, model of the reader, that is model of the mind, and so on and so forth. The problem with this kind of deflationist, I call them deflationist position about LLMs, is that, which parrotism is the most famous, is that well, they may make very, very bold claims where you usually find the word real. They have no real understanding, they have no real semantics, they have no real model of mind, they have no real model of words. That may be true or not. My problem with that position is that when you put that word real in the statement, you are coming back, you are calling back to life the ghost in the machine. Because you do not define actually in a very operational way what real means. Okay? So you presuppose that there is something that is metaphysically, intrinsically different in our intelligent, emotional, etc. behavior that cannot be modeled in any way, and those kind of stuff doesn't have it. I said that my philosopher of choice was Daniel Dennett, and he has been one that for 50 years has been fighting this idea that there must be something mysterious behind intelligence, emotions, phenomenal relation with reality, that is qualia and whatever. And these are errors of language, and that must be wiped out to have a real understanding of how stuff are. And I think this is the problem with many of these positions. They simply reintroduce the ghost in the machine. But anyway, this is a very complex debate, and I don't want to go on that. They can be also considered as cultural technology. This is an interesting paper that is written by a development psychologist, Alison Gopnik, with a set of collaborators, in which she was, anyway, criticizing the fact that they are not intelligent. They have not even the intelligence of a human baby, for various reasons. But she says they are actually a sort of cultural technology. The problem is that in this paper, she make a parallelism between LLMs and previous technical ways of automatizing the workings of culture, that is, for instance, libraries or photocopies on press. And I think that's an error. No? There is something more in LLMs than in a library as a technical stuff, no? I mean, not the, or in a photocopy machine, okay? There is this interesting paper by Harvey Lederman and collaborator, that is a philosopher working in Texas, I don't remember where, that criticizes this idea, making a point that actually they have meaning, also extensional meaning, not only intentional meaning that can be sort of accepted. So they have an external referential to the world because they derive it exactly like us from the language. And it makes some interesting philosophical discussion in this sense. But anyway, this is something that I want. Now, why am I introducing this idea? Because I think that we can use this idea of LLMs are a sort of cultural engines. And to make sense of them, no? Without saying they are really intelligent agents, they are, for me, yes, at least they understand language as much as we do it. Because understanding is not a mysterious property inside our brain. It's something that, as Victor said, can be assessed only in a conversation. And they do conversation. So why they do answer properly? They make errors. They hallucinate. Well, that's what we do. They have not all the properties that we have, but they have, anyway, the property of understanding what you ask them and answer in a proper way. So why not say that they don't? Why not say that they have a certain kind of understanding? Then we can also try to assess better this capability. But saying that they do not understand is really too much, in my opinion. But anyway, let's forget that. Are they cultural technology? They are for sure, because they read all the way in which we have, all the artifacts in which we have deposited culture in the World Wide Web or in the network in general. And so they read a lot of our culture, every aspect of our culture, the good and the bad. But that's what culture is. And this is an idea that was coined for the first time by a famous semiotician, Yuri Lotman, that proposed this idea of the semiosphere. And then there is another aspect that I will probably not delve into it. This is the idea of the model reader by Umberto Eco that is more proximal to my interest. And coming back to Lotman, well, starting from semiotics of language and of literary language especially, he started to reflect on what culture is. And he said, well, a culture is actually a sort of way of putting together all the text that have been produced in a certain culture that gives the language of that culture. The way, that is what can be said, what kind of ethical attitude can be taken about what is being said, and so on and so forth. So it's like a huge semiotic systems made of various semiotic systems, of course, language and written language, literature, but of course many other kind of languages, including imaging and so on and so forth. This is a system that is heterogeneous, of course, because we have different aspects of a culture that can be also conflicting. A culture is not one direction. There can be some moments in history in which the culture of a country or of a set of people can have a very strong ideas, but is never completely homogeneous. And this is what happens with LLMs. And then, interestingly, I found this paper that they wrote in 1969, in which he said, we must emphasize that collective intellect, that is synonymous of semiosphere. That is the idea that culture is like the intellect of the collectivity. As a model for having an artificial intelligent agent, has several advantages over individual intellect. That is, at the time, it was in the 60s, there was still no generative AI. They were still working the good old symbolic paradigm. You're trying to rebuild the intelligence of a single individual. Well, let's try to model the intelligence of collective systems, because it may be easier. And since collective intellect is a mechanism created by history of mankind, it is explicit because it's deposited into artifacts, texts, and so on and so forth. Its procedures are manifest in the language of culture, so you don't have to look at something that is internal to the brain that you cannot see, you cannot assess, you cannot measure, like beliefs and so on and so forth. It's recorded in text and in other semiotic artifacts, and it's not hidden in the human brain, something that we cannot look at directly. No, this is something that they wrote in 1969. And I think this is a really illuminating way of looking at LLMs now. And this is also why I think that, okay, let's jump this because I'm really too long. Maybe I would say something about this. This is why I think that they are an interesting stuff for us as digital humanists. Because what we do is trying to understand culture in its various manifestations using methods that are mostly computational. Modeling complex stuff like text, literary text, or language, or the use of certain adjectives in certain situations, or historical facts and whatever, okay? And they are deposited in culture because we start from looking at artifacts, mostly text, but not only text, and we know how to model this kind of stuff with these models now. We have models that work with images. Most of these images are created, all of these images are created by GPT DALL-E module. But also now we have the capacity of modeling video with the new models, and so we can do very complex stuff with this kind of models. And they, looking at this amount of complex artifacts, they learn how our culture works, okay? And so we can use them to test our ideas about culture. For instance, I do it for testing their understanding of narrative text. This is my work as a scholar. I try to assess how do they understand an history that is a story better, that is told in a story, in a novel, or short novel better, because it better control the cost of these experiments that cost a lot. And this is the kind of stuff I'm doing now. And that's why I also use this other metaphor of LLM as model reader, because this is an idea of Umberto Eco, that every text foresees its idea reader or model reader, and this idea reader is actually a sort of cultural agent that knows how to understand the text. And this is what, in my opinion, these models are. So that's what I'm playing with, trying to see if they can understand narrative implications, or if they can make what Eco called the inferential walks. That is, when you read a novel, at a certain point, there is something that may happen or may not, and you read to that point and imagine what may happen, and imagine possible paths. And then you read on, and you see that what the author decided, or the narrator decided to actually make happen in that world. And that book in which Eco devised this model is Lector in Fabula, that is one of the most famous books. And I'm testing are these models able to act as a model reader? What do they imagine, given a set of events narrated in a novel, can happen after? And believe me, there are really interesting stuff behind this. I'm working with my students. I ask them to indeed wait some passages in which there is a narrative turn, And then we test the capacities of Cloud, GPT-4, Gemini, and to see what happens. And sometimes it's really astonishing what the model says, because it's exactly what they imagine. Now I'm making a project on that, making a more substantial project, because these are kind of exploration for the moment. Or understanding the tech history and so on. This is what I know. And this is instead a work done by Ted Underwood, that is one of the most important people in the distant reading or computational humanities or literary studies better community that has been doing something similar. This is how trying to evaluate how much surprise you can perceive when reading a novel. That is similar to what I'm doing, but not totally overlapping. And he has done an experiment in doing that. You can read it in his blog. It has not published it as an article yet. But anyway, we are really too late for this. And I'm also working at this other project that is about using LLMs to understand the passages of a narrative text in which there is a free indirect discourse. This is interesting because I'm working in a project that tries to see if this is true, that is, or if there is any evidence, measurable evidence, that there has been a turning point in the turning of the century between 19th and 20th century, when from realism, most Western literature turned into modernism. And we have a lot of theories about that, and one of the most important things that they say, that we say as a literary scholar, is that, well, from the life of characters in a certain environment, you start looking at inner life of characters that clashes with its environment. So most of the modernist novels are looking inside what happened in a consciousness. That is a fictional consciousness, but it's not dissimilar from us. So I want to test this idea, and since one of the artifacts, linguistic artifacts via this is represented is using free indirect discourse, my starting point is, let's see if the model can trace indirect discourse in narrative text, in complex narrative text. Of course, I'm working in Italian narrative. And I am working with a set of collaborators, and we have very interesting results. Not entirely satisfying, I might say, but I must also work on the way we make the experimentations. Anyway, there are some interesting results. And the fact is that where there is a mismatch between our judgment about what indirect discourse is and what the model says, well, most of the time is because we were wrong. Actually, the model were more able to individuate passages of a free indirect discourse. Okay? And that's really interesting, because there is no way of saying for sure this is free indirect, like indirect discourse where you have signals. Okay? Now, why this is interesting for DH, and why I say that we are in face of a possible turn? Well, during my career, as I said, I traversed many idea of what humanities computing or digital humanities is. And I might say that at the time when I started, there was this idea, what I call the formalist paradigm. That is, we must formalize, one of the masters with Gigliotti was Tito Orlandi, the godfather of DH in Italy. And the first thing that he said to me when I went to his lab in Sapienza University was well, what is important in computing for the humanities is that you must formalize stuff. You must understand exactly what you are doing and translate it into a formal notion. Then you can translate it into a program, and possibly do not use any kind of graphical interface, write it directly in the command line using, at the time it was Snowball, that was one of the programming languages used for text processing, for string processing. You have to learn Snowball, I remember this idea. So we have to formalize. We have to have formal models of stuff. We have to understand exactly what we are doing, okay? And this has been the basis of what we have done for many years. Even text encoding is something like that. If you encode something using XML TI, for instance, for who knows what it is, explain what it is for who doesn't know. Well, if you mark up a text, say this is a paragraph, you are using a formal-like language to assess something. You are transferring your knowledge into a formal way of representing it so that the machine can use it for doing stuff. Okay? But what is happening is that you transfer your knowledge into a formal model. Okay? Then came the data revolution. So that, well, you don't have to, you have to not strictly formalize in a logical way, but you have to understand what can be measured, operationalizing, and then you have to count features, and then use algorithms that are mostly statistical probabilistic algorithms to understand stuff about text or whatever else. Okay? And we realized almost immediately that you cannot do with this approach most of the interesting stuff that we did in the 70s with literary text. Most of the theories of literature, for instance, that we have been fond of when I started being a scholar, that is the structuralist or semiotic way of analyzing text and so, cannot be operationalized. It doesn't work. You cannot find a way to operationalize notions like, I don't know, grammar structure of narrative, or notion like, how it's called, I don't remember, just a black hole in my memory. Anyway, and notions like that. I mean, you cannot, they tried hard to do that. But the effect was always, it doesn't work, also what? Because if you turn them into numbers, and you start by counting how many words there are in a text, scaling to these abstract aspects of textuality is impossible. And this is what, if you have read, probably not because it has not been translated, the last book by Moretti, Falso Movimento, his complaint is quite this. I tried hard to reconcile quantitative approaches with the beautiful theory of literature of the 70s and then 60s, formalism, structuralism, and I didn't succeed. And he complains a lot about that. But in my opinion, it was simply impossible, okay? Because they are too complex and abstract and interpretative prone kind of stuff to translate them into count how many words you have in a text and do complex stuff with that. Now, in my opinion, we are in phase of something new because these kind of models can do exactly that kind of stuff. They can work at the level of language. They read, okay, how many you decide, understand text, and they can answer to complex questions about text or, in general, cultural artifacts. You can discuss with them about everything. The most proper way to use a language model is not asking them something that is a piece of knowledge, but reasoning together. I have this set of conditions or data or starting point or these ideas, and I think they can be understood in this way. What do you think? And it answers, and you go on. And I do it almost every day now. Because when I have an idea, I try to discuss with it. These models can find new paths that you couldn't imagine. And believe me, this is not only for me that I am the last one that can say interesting things, but something that has been tested also in very complex domains. So my idea is that after the formalist approach, that's still my first love, so abandoning it is very hard. And you can see it still in action. For instance, all the linked data people, the people that is working on ontologies, are doing that kind of work, trying to build complex logical buildings based on logical ideas, or something like logical, to transfer what is not logical at all, or is only in a small part logical. And then the data-driven paradigm, that you count things and then use probability or statistics to understand something, but what we understand are not what we would like to understand, or are something new, totally new. You can understand very complex issues about literature in general using thousands of texts, but you cannot interpret a single text using that way. Or you can do it, but the results are very, very, in my opinion, most of them are not very interesting. Okay, let's, no? And now we have a tool, or a mechanical tool, agent, helper, that can work with us in solving this problem. The fact that cultural semiosphere is resistant to formalization, and has been resistant to formalization for years, even when the idea was trying to formalize the most of it. And this is something that has been translated into, transported into digital humanities or humanities computing. And that has been the real problem. Now, we have managed to do that really consistently, unless in a way that, I mean, in a sense, give up to most of the interesting stuff to do. Well, but generative AI doesn't ask to make formal symbols to represent what we are studying. We simply can give them the text, and then we can discuss with it about the text. They don't have at all logical capabilities. They can simulate or learn to do some kind of logic with very difficulties, also some kind of math. We know that one of the problems was, now not anymore, believe me. They do very complex math, much better than most of the people that is working on mathematics now. But they can, for sure, understand text and discuss and trying to find out things about text and culture and so on. So they can help us in making this operation of interpreting things, but being agents that are almost completely computational. Okay? And this is my idea, that we are in a phase in which we can really externalize some of the interpretative or hermeneutical work that we do working with culture and cultural artifacts to these kind of agents, without being asked to formalize or to translate them into a set of numerable features. And that's the idea of this turning point. Problem, limitation, a lot. They are not reliable. As I said, they can say many different things in different situations or conditions of an experiment. And they are prone to errors, what they call hallucinations. They have biases, parentheses, but this is interesting for us, because as Ted Underwood has said, one of the scholars that I was saying before, this is interesting for us because we want to understand culture, and biases are part of our culture. So the fact that they show biases is a way for us to understand those biases better. Paradoxically, when they say something, if you, I don't know, if you train a model using 600 text, and then you ask something about the role of women in society, you will, of course, have answers that reflect the cultural assumptions about the role of women in that moment of history. And that's, well, great for us. This is what we do as historians of culture, of literature, and so on, okay? So this is, for us, it's not a problem, it's a feature. And then, of course, we don't understand how they work, and that's a problem. And I said before, it's a problem that will not be solved probably very easily, and not at all completely, in the future, in the near future. But we can ask them why. Why you say so? This is interesting. You cannot understand which neurons are firing in a certain moment, but we cannot understand also for our brain. But we can ask why you say so. And the last models that are based on this idea of chain of thought, no, that is, they are reasoning over different possible paths of reasonings, and then they choose the correct one and answer, but you can see their reasoning. That's really interesting, because it's a model of our way of exploring the possible paths in the garden, to cite Borges. And two final slides. One, hallucinations are bad. Yeah, they are, but in a sense, if you work in an explorative setting, they are good. This is a paper that has been published a couple of months ago by a set of scientists in neurosciences, and in which they say that large language models exceeds human experts' capacities in predicting neuroscience results. And why, they say? Well, actually, if you present to a model a set of diagnosis results of analysis and so on and so forth, and ask him, well, what can be the issue given this set of data. The model explores different ways, also in even some very, minority paths, but they are more open than us. We are more prone to bias than what we expect. And quite this make them more reliable and good guesser at possible solutions to the problem. If you look backward looking, they make errors. But for the same reason that they make errors looking back, if you are forward looking, they explore possibilities. And in the results, this is a real experiment done with all the criteria of experiments, that is comparing the results with very thousands of diagnoses by medicians and so on and so forth. So it's a proper experiment, not like mine that I'm playing with narrative text. So, to close, there is still much to think. An experiment regarding the nature of this kind of system and the role as model or not of human cognition. But even if they are not proximal, and I do not believe they are really totally like us, they have properties of human intelligence, not the way that we have them, although they made us rethink most of the assumptions, for instance, about language. All the idea of having a strong syntactic, grammarly capacity hard-coded in the brain that was the base of Chomskyan linguistics. Well, this is a confutation of that idea. They don't have any grammarly knowledge. They learn to speak thousands, hundreds of languages perfectly well without doing any kind of grammatical error. And if that works, well, why should I assume that instead I have a sort of, don't know where, computational artifacts in my brain that compute syntagmas and so on and so forth, using non-contextual grammar or contextual grammars like the one that were imagined by the generative transformative. This is not only my idea. There was something like 10 papers by very important theoreticians of linguistics that saying that. But anyway, even if they are not, it's not the case that they are like us, like the protagonist of the Ex Machina movie, they offer, for the first time, a framework for testing in an empirical way hypotheses about mind, language, and culture. They are an open epistemological challenge for humanistic knowledge. And we need to invent and practice experiments, and we need to have good theory, and we must make a lot of experimental work. That's why I say that digital humanists are in the front of this endeavor, because we are used to sort of make experiments. And there is a huge space for curiosity and skills. Human scholar will be able to bridge this gap. So that's my point. Thank you.
Thank you very much, Fabio. I think you've given us a lot to think about. It was obviously it's a very complex topic and cannot be scaled down so very much either in a lecture of this kind. But I want to open to the public and allow you to ask questions or be critical or whatever you want to do.
Maybe you need the mic.
Yeah, thank you very much. It was really informative and very inspiring. The question I want to ask is, you had to go very quick through a part of the talk, unfortunately. And there you were starting to refer to different LLM models. Could you say something more about that? Because you mainly spoke about ChatGPT, and I was curious to what extent you're looking at other models in the research.
Yeah, well, the big models are more or less very similar in their behavior. I tested the same experiment usually with the three big models, the Gemini, Cloud, and GPT-4, or 401, because I'm playing with that in these last months. And I must say that more or less the behavior is very similar to this kind of problem. Of course, I don't test theory improving or something like that, so there can be difference, and you can read a lot of paper about that. This is the most common sport in this moment, testing this kind of stuff. But for us as humanists, I mean, they are very similar. What I can say that Cloud by Anthropic is more interesting in the way it mimic human conversations. Is capable of being more inventive, or to is less deep sometimes. These are simple, I mean, metaphors. Of course, I understand. But it's really engaging when you conversate with. Why GPT at a certain point it becomes boring. It doesn't. It's very hard to make him to force the model to make a move beyond his limits, and we know why, because they have been attacked since the very start. So they have created a strong cage in which the model must work on. But anyway, these three models are. When you use lower model with less parameters, things change totally. I've been testing models with 3 billion, 7 billion using my laptop. So in a local environment, that can be very useful. Also trying to force, but usually the gap of capabilities is very, very, very big. So in this moment, I still think that the scale law, the power law, that scaling the dimension of the model and the number of texts with which it has been trained is still very important. What is interesting is that for certain kind of tasks, you can also use smaller models, but you have to fine-tune them. You have to take the burden of preparing a set of question answers, for instance, and fine-tune a model that has been already trained. And for doing that, you need a lot of computing power anyway. Even if you use models around 10 billion parameters, I tested with something like 1,000 examples with 7 billion parameters models. That is an Italian model called Minerva. I just wanted to see if it was useful in any sensible way. And it took 2 days of continuous running on my laptop, and the results were completely useless. So I say, okay, why doing that? But maybe having enough computational power for fine-tuning models around 60 billion parameters, you can have interesting results for very specific tasks. For instance, identifying, I don't know, in a text, if it is in first person or third person ways. If you ask it to GPT, it works 10%. Doing that with a lot of text costs a lot of money, because using API with GPT or cloud, it can be very costly. You don't understand until you give the bill. you receive the bill. So I'm trying to use the smaller model for do this kind of experiments, and probably using a model of that dimension that is over 40 billion parameters can get good results. But anyway, it's very hard, because you have to. You need a very, very strong computational infrastructure for doing that. And it is not in my university, but even in Italy in general, in humanistic, especially in humanistic department, that's impossible. I'm working with my colleagues that are doing interesting stuff with LLMs at the engineering faculty, but anyway, even they can work with models like 30, 40 millions, not more. Billions, sorry.
Yeah, thank you for your enthusiastic view on generative AI. There certainly will be applications of using chat systems like ChatGPT to simulate cultural interaction. Yeah, I think that's definitely interesting. We have had this before, sort of the starting of AI was, for example, we had experiments like the ELISA, which is very similar. But I want to highlight one aspect of large language models that you didn't didn't insist upon, and that's their function as search engines. Yeah, sort of we have all these data using large training data, with the corrections, with the reinforcement learning, and the interaction with text and pictures, for example, text and sound, pictures and sound, etc. This enables new ways of retrieving and interrelating data, and I think this is the main use that we can also make of large language models in digital humanities. Yeah? Often the main research questions are things like reconstruct data, for example, yeah? Textual data, contextualizing them, maybe finding new ways of interpreting them, looking at semantic change, changes of cultural perspective and retrospect, etc., etc. And I think for tasks like these, large language models may be very, very useful, yeah? Assuming that one day we also have Italian language model and not only English, maybe also we have a Latin language model, etc. Yeah? So I think there are other applications beyond those that you have sort of highly motivatingly presented. But I think these other applications related to sort of their enrichment of search functions, yeah, and prompting basically is just a way of conversational search, yeah, new paradigms. I mean, that's what the big tech is working on, yeah, and so I think that's also one thing that needs to be pointed out.
Yes, it took 1 hour and a half for me. I should have added this, but I totally agree. Not only, I would say that most of the things that you were saying are similar to what I am saying. I'm more suspicious on the use of a pure retrieval engine, because we know that that's quite the direction in which they are more prone to hallucinations, and they can make up things. Of course, we have RAG, that these techniques, that for those that are experts, you know what it is, and for those that are not, I cannot explain what it is, but you can enforce them by looking at a certain set of, let's say, safe data before answering. So they are not only looking back in their semantic memory, but they are also using the amount of information that you give to them. So you can ensure that they don't say bullshit about something. But you cannot be always sure that this is not happening. Purely research, but instead the fact that you give them data and you say, well, let's try to explore the possibilities of understanding this data. And this is the kind of stuff that I'm trying to do. I do it with narrative text, that is something that is not interesting, but they are doing with diagnosis of neurological illness, and they are having great results, as they are for the analysis of radiologies and so on and so forth. So, and I mean, all the people that is working in this domain, very restricted, well, they are enthusiastic about it. I don't think that we will use them as a sort of new Google for simply retrieving specific stuff, because they are building again. Now, they are not retrieval machines. They are rebuilding that kind of stuff. And when you search something, well, we as humans, we want to be sure that we take exactly that text that was cited in that kind of book, so we can't so suspicious. But I'm not really interested in that. Instead, I would like to have them as a companion for exploring. Yeah. So, yes, most of what we said is almost completely overlapping.
Any other questions? I mean, there must be also some critical questions, perhaps. I mean, what about
also
society?
The ethical, for instance, the ethic.
I mean, what about Italian, for example? I mean, Gerhard already said it. I mean, it all depends on the data we have and which cultures are in this bubble, and which cultures are out, and which cultures will never enter it, probably, and so on and so on.
Yeah, and that's a problem, Elizabeth. That's really a problem. But one interesting stuff is, I've tested the Italian model Minerva done by a great scholar.
Yeah, could
this,
use another example.
No? And it's a small model, so you cannot compare with GPT, of course, because it's the biggest one is in this moment an 8 billion parameters model. That's, of course, like a toy compared to these big models. Anyway, and it's interesting. But at the end of the game, what these big models that I've read probably the same amount of Italian, but inside 90% of English of their billions of words, it's the same. I'm not really sure that adding or building models based on strictly monolinguistic cultures will give really, really new results. For instance, the first thing that I tried to do with this model, with the first iteration, that was GPT 3.5, that is the base of the first ChatGPT, was, well, let's read some poetry of early Italian literature, that is the Sicilian poetry. I cannot read it. I mean, I'm not anymore a linguistic, a literary scholar, and so I must confess that I lost all the knowledge about medieval poetry of Italian culture. So I said, okay, let's try, and let's make a paraphrase of the text. Then I had a conference, a talk in a conference organized by a Romance scholar. They were discussing about and it was happening 2 years ago, so we were at the very start of this process. And I saw, well, I present what how Jacopo Talentini has been paraphrased by GPT 3.5.
In Italian.
Into Italian. And they said, this is perfect. I mean, not one of our students that are students in Romance philology could do something better than that in paraphrasing not the Italian, because it is a Toscanized version of Sicilian language in the 13th century. So, and how many of them GPT can ever read? I mean, they are something like no more than 100 poems. And you will never read more than 100 because we don't have it, simply. So there's something deeper inside this model. I'm making really, I am metaphysical here. There's something deeper. They capture the way in which language works in a way that is resistant to the huge difference of the amount of linguistic data that you give to them. And of course, regarding the values that they can express, well, if you tell them not to use some kind of words, because in the US, and they are almost all US models, but that's not because they read text, because they are reinforced learn, teach to do that. So I'm not really, there are some experiments in doing that, and there are some people that say, well, they think in English. I don't know what it really means, they think in English. I don't know if it's even possible to say that we think in a language completely. For instance, these linguists that are taking the chance given by the LLM model to criticize Chomsky are saying quite that language and thought are two different things. And thought is something that is produced after language is something that we use to communicate thought. And it doesn't mean that thought is a language, like Fodor thought in the 60s. It's not at all a language. It's a more complex process of building something that then we externalize. In that sense, there is no sense in saying we think in English. Or we think in English or in Italian or in German or whatever, aloud, or at least in our mind, but then it's already at the end of the process of thinking. And this is what we can see them doing. And what is interesting, if you look at some of the models that are doing this new way of working, that is the O1 model, that is the thinking model, so to say. Also Google has released just 2 or 3 weeks ago one example of this, and there is a Chinese model that is great, and it is very small. I don't remember the name. You can use it, well, of course, you cannot compare something that has billions of euros and billions of parameters with a model. I don't remember the name. It's deep something. Anyway, and then it can work on a laptop. There is the biggest, it's 70 million parameters, so you need an M4 Mac with 128 gigabytes of RAM. Then you can make it work locally. But anyway, it is sometimes in Chinese, sometimes in English. when you look at the generation of the chain of thoughts, the tree of thoughts actually, it's not totally a chain, the tree of thoughts, you can find sometimes he thinks in Chinese, sometimes he thinks in. So this is the outcome. So it's true, there are. And another thing.
I don't have a clear.
No, but we must make experiments with this.
Yeah,
for instance, I was invited by Max Sinatra in Montreal in December, and I gave a conference similar to this one. And there was a PhD student that was doing an extensive experiments in that directions, using prompts in different languages, and asking the model to answer in different languages. So you ask him, what are the blah, blah, blah in English, but answer in French, or in German, or in Korean, okay? And making these complex experiments with many permutation of possibilities. So about ethics values, no? Ethical values. And the results were that actually there is not such a difference. I mean, if you ask him to say what would a German person answer to the ethical conundrum, and you ask him in English and tell him to answer in German, or there is not such a huge difference. So this is an experiment.
Yeah. Okay.
Probably is not totally. I mean, it's a small experiment because she has done a big work, but it's anyway a small. There are some thousand of queries. So we have to test it. I mean, we don't have to presume anything about it. Yeah?
I would like to allow one last question. And
no, because since it was my fault that I spoke too much, I can't stay, but we might go to they have to close.
They want to go home as well.
I would say here.
We want to go for meal.
I will try to make it short, but I think you highlighted the benefits of LLMs and the benefits of scale, I'd say. But what I'm thinking about when thinking about the usage of these things, my question is also, what are the costs? Ethical, culturally, but also ecological, because my understanding is that especially training these very, very large models, and they become bigger and bigger, comes with a huge amount of costs, financially and also ecologically. And in a constructive way, I would like to ask how can you balance this? Because I think there are applications that it's not useful to use these LLMs because maybe some other technology which is less cost intensive is more appropriate. But since it's the new next thing, I think everyone, it's the hammer for all nails or something like that. So maybe you can, I think there's no short answer to this question, but I think it's a question to be asked. Yeah. That's all I wanted to say.
Yeah, there is no short answer because it is a normative question, and of course, again, in face of normative question, you have values, beliefs, ethical positions that can not be shared even in this room, totally at least. My idea, okay, that is true, and so most of my talk was like the people talking and looking from the ivory tower. I don't care anything about how much it costs, what is the amount of energy that it uses. So it works great, it's interesting for me. I am enthusiastic. Then you say, okay, but look at what is happening under the hood, and it's destroying. That is true. Anyway, I am optimistic in general. Even I am a leftist guy, but I am an optimistic leftist guy, so I don't see that stuffs are necessarily going in the wrong way. So the optimistic stance is they actually are using a lot of energy, but they are making a lot of work for making it, them or it or the stuff more sustainable from the because they cost a lot, not because they are really caring about environment, as we have seen about diversity in the last days. So they don't care at all about this. They want to make money, and they want to spend less money as possible. And since spending less money is involved using less energy, they are trying to make them more efficient. The new NVIDIA graphic cards that are more powerful than the A100 that have been used for the first round of training of these models are much more powerful and they consume less energy. So probably in this direction they will find a way of solving the problem, or at least coping with the problem. The second argument that I usually use is, do you know how much energy costs the CERN, the synchrotron, for understanding how bosons of Higgs works in the ultimate level of our reality? Costs a lot. Are we making this kind of argument against the synchrotron of CERN? No. Well, for two reasons. First of all, because that's not a private endeavor. So we are against what is happening because of the fact that it's done by Microsoft, OpenAI, or by Google, or by that awful guy that is Elon Musk, and so on and so forth. While we don't say the same thing for other kind of endeavors that are also very expensive in terms of energy, in terms of money, because it costs a lot of money. Building the new synchrotron, it costs tens of billions of euros. And they are building it. And you could help a lot of people with that tens of billions. And for discovering what, if the string theory is true or not. Well, they still don't have an experiment for doing that. So, I don't know, yes, I'm closing. So, my idea is that, yes, there are these problems, but we have to put into the balance what we can learn about ourselves and culture and nature and whatever using this kind of technology and what we are paying for doing that. And we pay a lot for a lot of stuff that is really useful, useless, or even harmful, like armor. So I don't know if this is something that can sort of not solve all your conundrums, but say, okay, let's look at the big picture, and maybe paying for that is better than paying for building, I don't know, arms or something like that. And finally, yes, the problem is that we are giving money to OpenAI and to all the other bad guys. That is true, but remember that they started as 30 guys, just graduated from Berkeley, with Sam Altman that was a manager 5 years ago. I mean, in that moment, it was possible for instance, big funding institutions to say, oh, okay, this is something that is happening, and we must enter into and build, for instance, a public European infrastructure for doing that. But nobody cares about it. Cared and cares now. Why? I remember saying, and other people say, why don't we think to a CERN of AI for Europe? Now we are complaining about the fact that we are in the end of Sam Altman or the other bad guys.
We knew that ages ago.
They are all Americans, now they are friends of that. Don't use bad words. But yes, we are complaining. But it was 5 years ago. It was possible to go into that game, and nobody did it. So, in a sense, we are still have time for doing that. But of course, there must be the political will to fund research in that direction.
Fabio, I think you have given us more than enough to think about, and I'm really happy that we had a discussion as well, and also different viewpoints. I think there are many, many different viewpoints still underground, but we don't have the time to bring them all up. I think the most important is that we start to think about it in all sorts of directions. I mean, enthusiasm is great, but we need to think about and ask and question and be critical and ask a lot of other important questions. So I think we need to open this discourse, and we need to keep it active, and input like this is very useful and helpful, and I thank you very much for this big contribution.
It's been a pleasure and an honor for me.